Welcome to the deep dive. Today, we're getting into something that's often overlooked, but honestly, it's absolutely critical in electronics. We're talking about the capacitor. You could think of it as a kind of silent workhorse, quietly doing its job inside almost every device you use. Our mission here is pretty simple. Take our source, capacitors, principles, types, and applications, and pull out the key stuff, the important bits. Basically, give you a shortcut to understanding something really vital in the tech that surrounds us.
Exactly. And kicking things off, the source defines a capacitor pretty clearly. It's an electronic component, and its main job is to temporarily store electrical charge. It's not like a battery storing energy long-term with chemistry. This is more physical. Quick charge, quick discharge. It's basic structure. Really simple, actually. You've got two conductive plates, think metal sheets, and they're separated by an insulating material. That insulator has a specific name.
A dielectric.
Okay, two plates and an insulator. And its main job is storing charge. Storing and releasing charge, yep. That's the core function. And we measure its ability to do that, its capacitance, in a unit called the farad. We just write it as F.
Right, the farad. So, these components, they store and release charge, but it sounds like there's a huge variety of them out there. Okay, let's unpack this a bit. Where exactly are these things making a difference, and, well, why should we care? What makes them so fundamental?
Well, that fraud measurement isn't just a random number. The source makes it clear it's tied directly to the physical construction. Three main things determine how much capacitance you get. First, the size, the surface area of those conductive plates. Bigger plates mean more room to store charge, so higher capacitance. Makes sense, right?
Yeah, more area, more storage.
Okay. Second, the distance between the plates.
Mm-hmm.
The closer they are, without touching, of course, the stronger the electric field between them. And that boosts the capacitance, too.
Closer means stronger field, higher capacitance. Got it. And the third thing?
The third, and this is really key, is the type of dielectric material used, the insulator itself.
Ah, so it's not just keeping the plates apart, it actually does something.
Oh, absolutely. It's much more than a spacer. Different materials, air, paper, ceramics, special plastics, you name it.
Yeah.
They affect the electric field differently. There's something called a dielectric constant. Basically, how well they support that electric field. Higher constant means more capacitance for the same size and spacing. And it also determines the breakdown voltage, how much voltage it can handle before, well, zap, the dielectric fails.
Breakdown voltage. So you can't just put any voltage across any capacitor.
Definitely not. That's a critical spec.
Yeah.
Get it wrong, and the capacitor is toast. And that's why you see so many different kinds. They're optimized.
Yeah.
Different materials, different constructions for different jobs and voltages.
That really clicks. Okay, so knowing the physical stuff matters. What are some of the main types the source talks about? What makes them different in practice?
Right, the source covers several key types. A really common one is the electrolytic capacitor. These guys are known for packing a lot of capacitance into a small space. High capacitance density. They do this with an incredibly thin dielectric, usually an oxide layer formed right on the metal plate. But there's a catch. They're polarized.
Polarized, meaning like a battery, positive and negative ends.
Exactly. You absolutely have to connect them the right way around in the circuit, positive to positive, negative to negative. If you hook them up backwards, they can overheat, bulge, even pop quite dramatically sometimes.
Okay, so powerful but need careful handling. Where do you typically find those?
Power supplies are a classic example. They're fantastic for filtering, smoothing out the DC voltage after it's been converted from AC.
Filtering. Well, we should circle back to how that works. What about other types, maybe smaller ones?
Yeah, definitely. Then you have ceramic capacitors. These are usually tiny, often look like little brown or blue blobs or rectangles. They offer lower capacitance values compared to electrolytics, but they're not polarized, which is handy. And they're really good at high frequencies. Great stability, too.
High frequencies, so for faster signals.
Precisely. You find tons of them right next to computer chips, microcontrollers. They act as decoupling capacitors. They filter out high-frequency noise and provide little bursts of energy right where the chip needs it, instantly, like tiny local power reserves.
Okay, so thousands of those little guys keeping things stable on a circuit board. Any other major types?
One more the source highlights is film capacitors. These use thin plastic films like polyester or polypropylene as the dielectric. They're known for being very stable, reliable, and having low electrical losses. Good precision. Because of that, you often see them in audio equipment where you need clean signals, or in timing circuits that require accuracy.
Interesting. Electrolytic for bulk storage, ceramic for high-frequency decoupling, and film for precision. It really shows how tailored they are. You mentioned filtering with electrolytics in power supplies. Can you walk us through that? How does a capacitor actually smooth voltage?
Sure. So imagine you've just converted AC from the wall into DC. It's DC, but it's often bumpy. It has ripple. The voltage isn't perfectly flat. It goes up and down a bit. You place a capacitor, usually a big electrolytic one, across that DC output in parallel. When the incoming voltage peaks, the capacitor charges up, soaking up that extra energy. Then, when the voltage starts to dip, the capacitor discharges, releasing its stored energy back into the circuit.
Ah, so it fills in the valleys using the energy it's stored from the peaks.
Exactly. It acts like a small, very fast-acting reservoir. It smooths out those bumps, giving you a much cleaner, more stable DC voltage for the rest of the electronics to use.
That makes perfect sense, like a little buffer tank for electrons.
Yeah.
Okay, what's another really key job they do?
Timing circuits are another huge area. So many things rely on precise timing. Flashing lights, creating delays, generating the clock pulses that run computers. You often combine a capacitor with a resistor. That's called an RC circuit resistor capacitor. The resistor controls how fast the capacitor charges up. The voltage across the capacitor rises predictably over time.
Predictably, because the resistance and capacitance values are known.
Right. You know the values, so you know the time constant. You can calculate exactly how long it takes for the voltage to reach a certain level. And when it hits that level, that voltage can be used to trigger something else in the circuit, turn something on, turn something off, start the next step in a sequence. So by choosing the right resistor and capacitor, engineers can create very precise delays or oscillations.
Wow. So from power smoothing to setting the beat for digital logic, these things are fundamental. It's amazing